My name is Paul Butcher. I am the floating head in the triangle at the bottom of this screen, and I'm going to talk to you today about fuzzing for airworthiness security. So very quickly, I work for AdaCore. I'm a senior software engineer. My background is mainly real-time embedded software development, mainly around safety, mission, and security critical projects. AdaCore is a company that's been around for over 27 years now, and we make software development tools. And I'd encourage you, if you want to learn more about the company, please go and look at the website. So what do? Well, we produce software development tools. The main tools that we produce are compilers. They are compilers for Ada, C, and C++ across multiple operating systems on multiple processors. But we also develop lots of other tools, and the ones I'm going to talk about today are the fuzzing technology we've been working on. And you can't really talk about that without bringing in the compiler toolchain and our coverage capability. I just need to quickly tell you that this work has been done through a research project in the UK called HICLASS. And there's a link at the bottom of this slide that will tell you all about it. But this is a joint industry and UK government invested program looking into cybersecurity within civilian aerospace within the UK. So what do we actually mean by airworthiness safety? Well, this is all about ensuring that every component of the air vehicle and all the systems that make up the air vehicle, should any of them fail, that the risk of that failure leading to a safety hazard that can have an impact on any of the humans involved in that air vehicle is as low as reasonably practical. And obviously this is really important. We want to make sure our aircrafts are safe. But we also need to come up with we need to be able to argue that they're safe. And what I mean here is that we need to be able to convince the regulatory bodies, namely the organizations like the FAA, who cover the airspace within the US, and EASA, who cover the airspace within Europe. We need to convince these people that our systems are safe. And there's many ways of going about doing this. One mechanism is to do something like what we've got here, which is goal structure notation, which is a formal way of breaking down an argument. So you would start off with a top level goal that would say something along the lines of, my aircraft is safe because the risk of a failure leading to a safety hazard is as low as reasonably practical. And then you'll break that down into lots of sub goals and you'll build up evidence to support your argument. And what this diagram is showing you here is that we're at the point in the argument where we're arguing that our software system within our avionics is safe. And the way that we can do that is by using guidelines that have been stipulated by these regulatory bodies as being an acceptable means of compliance with the requirements that they've set out. And one such set of guidelines is DO178C, which is all about how you produce safe software for flight. And the industry is very good at doing this. They've been doing this for a long time. The processes are very mature, which you'd like to hear. But you may ask the question then, if we've got very mature safety processes within aviation, why do we need a airworthiness security process? And one article I found when researching for this talk was a keynote that was given by Robert Hickey from the US Department of Homeland Security, who stated during the CyberSats conference in 2017 that his team managed to establish a software presence on board the avionics system of an aircraft. And what was fascinating about this was that they had achieved this with the aircraft sat on a runway at Atlanta City Airport. There was no insider threat, and they didn't need to have any sort of physical contact with the aircraft. This wasn't a remote attack that they'd established. And the report goes on to talk about how the vulnerabilities that were exploited within the avionics systems it would appear that they were well known about. And you may immediately want to ask then, well, why weren't they fixed if they were known about? And I'm sure there's plenty of reasons. I've come up with 5 potentials here. The one that I think is more than likely to be the explanation is to do with number 5, the cost. And Robert Hickey did go on to say during that keynote address that the cost to change one line of code on a piece of deployed avionics equipment is $1 million US, and it will take a year to implement. So you can see that it's just not scalable, and how if you've got a complex vulnerability you need to patch on a deployed system, it's going to be very expensive and it's going to take a long time. So one of the reasons this situation could have happened may be due to the terminology within the safety processes. And one of the main terminologies we need to understand early on is what a failure condition is. And this is all about the result of some malfunction that has happened, which has a direct impact on the vehicle that could lead to a safety hazard. And it does go on to say in this description here that that could be caused by an external event. So you may think, well, that surely should cover cyber attacks. But when you dive deeper and you start to look at the definition of an event, it's more about environmental conditions like lightning strikes or bird strikes, and it doesn't really cover cyber attacks. So if the safety standards were never written with cyber security in mind, what do we do? What do we need to do about it? Well, the regulatory authorities asked two working groups, namely the RTCA and EUROCAE, to come up with a solution. And what they did was they produced two new sets of guidelines, namely ED 202A and DO 326A. And the first thing they did was introduce this new terminology, a threat condition. And this is similar to a failure condition, but here we are specifically talking about intentional unauthorized electronic interaction involving cyber threats. So in the security world for aviation, we talk about threats as being human initiated, and they are intentional acts. And in safety terms, we have events which are more environmentally occurring, and failures and errors which we consider to be accidental. The process itself is quite complicated. It's way too complicated to go over in any great depth today, but it is made up of these 7 phases. It's not a linear process. It jumps all over the place. But stage 1 is all about ensuring that you can come up with a way of stipulating exactly what you're going to do. This is your plan for security aspects of certification. And this includes what you're going to build, how you're going to ensure it's secure, and how you're going to test that it's secure. And that needs to be agreed by your regulatory authority or some auditing person who's going to work on their behalf. One aspect that's of particular interest is security development, and that covers something called security verification. And when we break that down further, it includes security effectiveness assurance and identification of vulnerabilities. And this is kind of why I'm talking about this today, because fuzz testing can play a key role here. The process encourages the use of defense in depth, like a lot of security standards do. And here, where we've identified our security assets, we layer them with security measures and ensure that we can argue independence. And fuzz testing can play multiple roles at this point. It can assess the effectiveness of those security measures, and it can also identify them, because it can identify bugs within your software. And if we can argue that we can exploit those bugs, then they become their vulnerabilities, and we either need to fix them, or if we can't, we have to mitigate them with security measures. And at this point, that software component becomes an asset, a security asset. The guidelines supporting these standards bring in a new terminology, a new term called security refutation. And this is all about refuting the claim that your system is secure. And that very deliberate negative take on traditional verification testing is intentional, and it's designed to put you in the mindset of the attacker. So refutation encompasses activities, and this is quoted from the guidelines, such as security penetration testing, static and dynamic code analysis, formal proofs, and fuzz testing. And this is interesting because fuzz testing isn't a technique that's widely used within this industry. So within HICLASS, we have a working group that's looking at these standards. And one of the first things that we did was perform a gap analysis. And that resulted in an issue saying that, well, the guidelines around refutation testing are quite weak. And some of the points that were made may resonate with the people listening today, in that when you first look at fuzz testing, you may have gone through the similar emotions to what I did, in that you first of all think, wow, this technology is fantastic. And then you immediately think, but how long do I run it for? How do I measure quantity and quality? What am I testing here? Is it a unit level or a system level or something else? And what about the choice of programming language? How does that affect it? So Ada has a very rich runtime environment, and we can switch on multiple constraint checking capabilities, and we can detect things like buffer overflows and raise exceptions back to the application. Languages like C, you may need to include additional anomaly detection capabilities, like address sanitizers via the compiler switch. Ada also supports things like design by contract, where you can put pre and post conditions around your subprograms. And then this is really interesting for fuzz testing, because this is where we can start to look more towards fuzz testing for functional correctness, in addition to just finding crashes in your system. But so industry is asking for guidance through the HICLASS group. So what we did was we produced a technical paper called Guidelines and Considerations Around Refutation Objectives. And the main part of this report contains 30 considerations. And then we've included an annex for fuzz testing, which takes each of those considerations and provides guidelines around them. One of the things we recommend within this is that when you want to stipulate how you're going to complete your fuzzing campaign within your plan for security aspects of certification, you need to ensure that you can do it in a way that you're going to convince your regulatory authority that you're providing the security assurance to the correct level. And what we recommend here is that you come up with a starting criteria and a stopping criteria. Now, the starting criteria is a focus on the starting corpus of the fuzzing campaign. And one of the things we suggest within the report is that you should aim for 100% statement coverage. And there's different ways you can achieve that. One, you may find that the program already is doing unit testing and already has that level of coverage, and they can just take those unit test cases and turn them into a fuzzing starting corpus. Otherwise, you may have to go down the route of doing smart grey box fuzz testing to produce your corpus, and then you can start your actual fuzzing campaign. The stopping criteria is where we recommend that you come up with an algorithm that determines the duration of time you're going to run the campaign for. And we've got an example that we provide within the paper. But the factors are going to include the test execution speed that you're achieving, the security assurance levels of the security measures you're targeting, the cyclomatic complexity of the application you're testing is going to play a key factor, whether that's a McCabe analysis or something else. And then you need some way of measuring the complexity of the input data itself. So I just want to talk to you about the tool that we've been working on that's trying to satisfy these objectives. It's called GNATfuzz. We have a fully working prototype that I'll demonstrate to you. We're basing the tool on AFL++. This is our mutation engine that we're using. And I just want to take this opportunity to give a big shout out to everyone that's involved in AFL++. It's a fantastic community, and we've been very grateful for the help we've received there. And if you open the hood of GNATfuzz, it's made up of modules, some of which we already had at AdaCore, others we've had to develop. libadalang is a tool that understands the semantic analysis of the Ada programming language. And we use this tool to build up abstract syntax trees of the user's Ada program. And then we can automatically generate all the code we need to create the fuzz test harness. We can also use this technology to build our starting corpus. So we take the types associated with the parameters of the subprograms that we've identified as our test injection points. And then we create values based on those types, and we stream them into test cases via Ada's built-in streaming mechanism. And this technology is also used to build to create the build scripts for executing the test harness. Quite early on, we produced a GCC compiler for vanilla AFL, and this is the compiler pass that adds the instrumentation around the basic blocks. We've since merged that to work with AFL++, and we've upstreamed that to the AFL++ GitHub repository. So we use that in conjunction with our GNAT Pro compiler to build a AFL fuzzable test harness. We built an AFL runtime library for Ada that, on one aspect of it, is that it does a similar thing to the normal C runtime of AFL, in that it provides an Ada binding to the AFL modes of deferred and persistent, and the other variations that AFL supports. And then it also takes care of the encoding and decoding of Ada values to our binary test case files. So we try and do this in a very fuzz test efficient way. And what I mean there is that we try and pack our test cases as tightly as we can, so that the mutations are as efficient as possible, and we're not wasting mutation cycles on data that isn't valid. GNAT coverage is our coverage tool. It supports statement decision, MCDC. Within the fuzzer tool, we run a dynamic coverage. So we produce a coverage build, and we execute all the test cases within the AFL queue through that coverage build. And then we feed the coverage analysis back to the user in real time. We've also been experimenting with the symbolic execution add-on. We've looked at various symbolic execution capabilities, and it was during the FuzzCon presentation that Sebastian gave in 2019 that I was introduced to SimCC, and we've since taken that capability and we've made it work for Ada, so we can use the SimCC compiler pass alongside our GNAT LLVM front end, and we can then embed symbolic execution runtime into our fuzz test harness, and this gives us even more test cases. This is more prototype technology, but this is very much will end up in our final product. And then we've also used the AFL custom mutation library API quite extensively, and again, this is a fantastic feature of AFL++. So here we can intercept the byte representations of the test cases, and we can mutate them with a full understanding of the Ada types that they represent. And we're also looking at doing a dynamic corpus generation within this capability, and this allows us to produce the starting corpus on the fly and not have to worry about generating files, which makes it a lot quicker. So this whole capability is tied into, well, it can be invoked from our GNAT Studio front-end integrated development environment. So here we can analyze Ada code and we can identify what can be fuzz tested. So at the moment, we only support scalar type. And then we can automatically generate the test harness, and we can execute the test and get dynamic feedback. But like all tools at AdaCore, they're also fully supported from the command line. So they're tool chainable and they can be invoked from DevSecOps pipelines. So I'm just going to give you a quick demonstration of what that looks like. So we're going to launch GNAT Studio on an Ada project. So here we can see that, yes, it is indeed an Ada project. There's some Ada package specifications and bodies. And what we can do is we can launch the GNATfuzz menu option at the top, and we can ask the tool to analyze all these programs and tell us what we can currently fuzz test. So this is going to look through all the types and find all the scalar types of subprograms. And for each of the ones we can fuzz test, we now get an option to say generate fuzz test harness. And all of the fuzzable subprograms are listed. So if we take one and generate the harness, then we're immediately given the option to switch to the test harness project. And we're now wrapping that user project around within our fuzz test project. So you can see that the user project is still there, but now we can fuzz test it. This is an example of what a stopping criteria looks like. It's a very simple one. It just says stop when you reach 100% coverage. But we can make this as complicated or as simplistic as the user wants it to be. So if we go ahead and launch the fuzzing session, so now we are producing all of the builds in the background for AFL for coverage. We're also producing a build to generate the starting corpus. So we've generated 729 test cases in this example. We've run the corpus minimizer that's built into AFL, so we can reduce it down to 4. And then we're going to work out how many nodes are available, spin up the fuzzer. So now we're executing AFL fuzz on 4 nodes, and we're already getting dynamic coverage back. So we can see it via this view, or we can also go and look at the code files themselves, and it will decorate the lines of the code that have been hit by the fuzzer. So red means we haven't hit this line, green means we have. And then in the fuzz crashes, you can see that the test cases that have crashed the system or have caused the Ada runtime to raise constraint errors are being listed here. So I'm just going to skip ahead a bit. So with each of these test cases, we can expand them, and the tool will now, these are binary test case files, but the tool can decode them on the fly and show you a human readable representation of the data that's inside of them. So here we can see the types of the parameters and the values that were fed in that caused this error. And what we can do is we can execute these tests by clicking on them, and it will rebuild the software in debug mode, execute the test, fire in that test case, and it will take us to the point where the exception was raised. And over here we can see the call stack, and we can use GDB, which is built into the IDE, or as our debugging environment to work out what went wrong. And in this particular case, we can work out that actually that summation and that multiplication causes an overflow. So at this point, we can go ahead and make the fix, and we can recompile, and we can execute the session again. And we quite like this because we're very much in support of pushing the technology as close to the developer as we can, as part of the shift left movement, if you like. But we do thoroughly expect this capability also will need to be supported on a back-end server for longer running test executions as well. Okay, so that's a very quick overview of the tool. And this is a list of all the references of things that I've referred to today. Thank you very much, and I'm open to any questions.